Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue our new series on time constants. Recall from last week when we showed how time constants can be used for a variety of time-dependent behaviors in science and in web handling. If you have not done so already, please view that show. This week, we are describing the simplest and best known time-dependent behavior, and that is moisture changes in paper webs. Now, before you tune me out, this exact same behavior is also seen on temperature changes in webs. But because temperature is much less studied, this is the best place to begin. The concepts given here are also fundamental to when we move on to moisture and temperature changes in a wound roll in following episodes. We will be exploring several web moisture applications in this show. The first is conditioning of paper prior to testing. Then we will briefly discuss just some of the challenges of measuring web moisture. Also note that we have similar challenges measuring web temperature. Then we will discuss two winder defects that directly result from moisture changes: the splice offset, and web breaks during winder stop. Let me elaborate more about moisture and temperature. Fick's law of diffusion applies to both moisture and temperature. Notice the only tiny and trivial differences are the variable of concern is temperature for most materials and moisture for paper and certain plastics. Note that we will label diffusion constants different as well. In the case of temperature, alpha is the coefficient of thermal diffusion, and in the case of moisture, beta is the coefficient of hygroscopic diffusion. Two systems understood for the price of one. How nice! Now let's clarify starting and ending conditions. As it turns out, it doesn't matter whether you're moisturizing or drying, heating or cooling. It doesn't even matter what the endpoints are, at least in principle. Thus, you can use time constants to define a moisture change due to moisturizing from 6 to 10% with equal ease as going from 4% to 6%. Similarly, you can use it to define a moisture change due to drying from 10% to 6% with equal ease as going from 6% to 4%. Conditioning of thin paper to equilibrium with standard lab conditions of 20 degrees C and 50% RH is important prior to testing to normalize the results. This is especially important for basis weight and strength because they are so very dependent on moisture, but it's also important for just about any other test. The time constant for thin paper exposed on both sides in still air is something like 1 minute. I have seen preconditioning time specified from everything from 6 minutes to 24 hours. That's quite a range. We will show you how to get time constants for a specific application shortly, so stay tuned. While it would seem to be super conservative and even impractical to wait 24 hours to do testing, I will come to TAPI's defense in two ways. First, paper weights can vary from lightweight tissue to heavy board, some 2 orders of magnitude. Second, if you read the fine print, there's an exception, but one that requires you to do a little work. That work is quite easy, as we will see next. Getting time constants is easier than you might think, at least in principle. Basically, all you have to do is weigh a sample exposed on 2 sides as a function of time. Then we fit an exponential curve. Finally, we extract the time constant from the curve fit. In the example shown here, the sample initially had a 7% moisture, but will equilibrate to 5% given enough time. The gold standard for moisture measurement is to weigh, then dry, then weigh. However, there are many complications to this simple idea. First, there's no such thing as zero moisture in paper. Rather, zero is a definition of the weight after drying under specified conditions. There is still some moisture remaining. Also, it is not possible to get a weight at time t equals 0, because it takes some time to move the sample from its original place, such as buried a few layers deep in a wound roll, to a new environment, such as a test lab. As such, getting bone-dry weight is easier than getting moisture levels for these reasons. There are many other subtleties that I don't have time to cover here, but this is at least outlining the essence of the procedure. For those wishing to read more, my article below is both a novel bit of research as well as a review of the state of art. So now let's move on to the third of our 4 moisture application examples, the splice offset in the wound roll. That happens when the paper is wetter than equilibrium with the winder environment. The first thing to note is the winder runs far too fast for paper to change moisture during run. Specifically, the material sees exposure to air for only a couple of seconds at most, far too short to matter given a 1-minute time constant for that system. However, once the winder stops, it has way more than enough time for the paper to expand. Thus, the already cut material between the slitter blade and the wind-up expands wider than the material that is wound at speed. That makes an outsy ring on both sides of the roll, and thus is not really an offset, but rather a wider width for a few wraps, representing the length of the exposed web run from the unwind to the wind-up. Something totally different happens if the paper is wetter than equilibrium with the winder environment. Now when the winder stops, the paper shrinks, something like a millimeter or more on a wide machine. That causes the paper to tear on the outer slitter blades, and that may well cause a full web break once the winder attempts to restart. I hope you've enjoyed this discussion of just 4 of the many challenges when paper is not in moisture equilibrium with its current or lab environment. Stay tuned for next week's show when we describe moisture changes in paper or other hygroscopic materials in a wound roll rather than in the web. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.